Today we're continuing our discussion on eigenvalues and eigenvectors into this idea of diagonalizing a matrix. When I introduced eigenvalues and eigenvectors yesterday, I talked about this need to finding the power of a matrix A, and we will see that diagonalizing a matrix is the way to find powers of a matrix in an efficient way. Now, what does this diagonalization actually mean? It means that we can have a matrix A and write it in the form x lambda x inverse, where obviously the matrix X is invertible because I've written X inverse. But the point is that the matrix lambda is a diagonal matrix. So what we'll do today is talk about how to get to such a form and why such a form is important. So if we have a matrix L lambda that is diagonal and our matrix A splits into a product of three matrices in this way. Remember, we're still in the case of square n by n matrices, so all of these matrices are n by n. The matrix A doesn't have to be invertible. Remember, if it has a zero eigenvalue, then it's not invertible. This lambda will come from the eigenvalues. So sometimes a matrix does admit this kind of factorization, sometimes it doesn't. We will talk about the cases when it does admit this factorization. So the first question is, why would we even want to represent A in this way? So why is this factorization useful? And then I will explain how to find it. So as noted yesterday, we talked about powers of the matrix A. Let's look at what is A squared if we know that A splits in this way or factorizes into this form. So we call it diagonalized because, let me mention this before I go into A squared. The reason we call A diagonalized, if we can write it in this form, is because I can multiply. So this is like how to modify A to get to a diagonal matrix. So via this matrix X, I can actually I can change somehow the matrix. So remember that matrices always represent some kind of transformation. So this matrix represents a transformation or linear combinations or linear operations or row operations on the columns of A, whereas this matrix will represent operations on the rows of A. So somehow with elementary operations on A and elementary operations on the rows and columns of A, we get to this matrix lambda, even though elimination is not the way to find this factorization. But the point is that we can write A, or we can get to a lambda from A, to a diagonal lambda from A, via some invertible matrix X. Then we will have some very interesting properties that come for the powers of A. So this is why we call it diagonalized. We can multiply A by some matrices, by some matrix X and its inverse to get to a diagonal form. That's where diagonalization comes from. Okay, now what about the powers of A? Let's look at A squared. So obviously A squared is A times A. And for each of these A's, I can use this factorization that I have at the beginning. So that's X lambda X inverse. That's from the first A matrix. And from the second, we have X lambda X inverse. Now what happens here is that I can carry out the multiplication. So the associative law of multiplication allows me to multiply these two matrices first. Well, those two matrices give me the identity matrix. So really what I have is x lambda lambda x inverse. But lambda times lambda is simply lambda squared, so we get x lambda squared x inverse. So let me write those together. A squared is x lambda squared x inverse. So this is very neat. I understand that this is how I take the square of a matrix, and I just need to square a diagonal matrix. So maybe this is a place where I need to pause for a moment and remind you that the square of a diagonal matrix is something very easy to find. So if our matrix lambda here is diagonal, I'll use a 3 by 3 case, but you will understand that it works in the exact same way in higher dimensions. So if I have lambda 1, lambda 2, let's say lambda 3, with some diagonal terms along the diagonal, with some non-zero terms, they could be 0, but if there is a non-zero term, then it is along the diagonal. And everything off diagonal has to be 0. So then the square of the matrix really will just multiply these lambdas by the corresponding value. So actually it squares the diagonal terms. This is only true for diagonal matrices. For non-diagonal matrices, the off-diagonal terms do not allow for this to happen. So you see, the powers of a diagonal matrix are very easy. You just take the powers of the diagonal terms. And similarly, if I want to find the inverse of a matrix, well, I just need to take the reciprocals along the diagonal terms. And we've seen this in inverses of diagonal matrices. So you understand here, in trying to compute the square of A, if I have this factorization, I just put a square here and I put a square there. So I just need to square lambda and then carry out that multiplication. If I need this for a to the power 100, then it's definitely worth it to find the factorization x lambda x inverse, take lambda to the power 100, and then multiply again if I actually need a. Although any operation by a can be applied by repeated operation by x inverse lambda and then x. So I could carry out the multiplication, or I don't have to, that's okay. So then from here, it is very obvious that a to the n equals x times lambda to the n x inverse. So the moral of the story is that if A can be diagonalized, so not every matrix admits such a diagonalization. You cannot find an x for every matrix A. But if A can be diagonalized, then the powers of A are given by x lambda to the n x inverse, where obviously A was just x lambda x inverse. So we see that this diagonalization gives us the powers of a matrix A right away. Now we also saw, or where will this come from? Okay, let's talk about how to find the diagonalization. So assuming that the matrix has a diagonalization, how to find it? How to find the diagonalization of A. And again, assuming that A can be diagonalized. I'll mention briefly when A cannot be diagonalized, although all the examples that we will see will be of special A's that do admit diagonalizations. So how to find the diagonalization of A? We're in the world of eigenvalues and eigenvectors, so these two things will have something to do. with the diagonalization. So assume that A has, so we're assuming that A is n by n, so now n stands for the size of A. So assume that A has n linearly independent eigenvectors. Okay, so what does this mean? Let me write the equations for these n independent eigenvectors. So the first vector being x1, I know that when I do A times x1, I will get lambda 1 x1 because that's an eigenvector with a corresponding eigenvalue lambda 1. Then for the second eigenvector, I have ax2 equals lambda 2 x2. And so on, I continue all the way to xn, right? So for each eigenvector, I'm getting, when I multiply by A, I'm getting a multiple of that vector, and the multiple is sort of directed by the eigenvalue. Now, how can I represent all of this in just one multiplication? So remember, x is a column vector here. When you multiply A times x, you get another column vector. So if we put these vectors as the columns of a matrix, X, for example, so let's say A times, now I will put these vectors x1, x2, all the way to xn in one matrix. I will call that matrix X, the eigenvector matrix. Why the eigenvector matrix? Because it consists of the eigenvectors of A. So now what happens is we can carry out this multiplication in the form matrix times column. So one column at a time. A times x1 gives us the first column. That's lambda 1 x1. And that's the first column of the product. Then the second column is lambda 2 x2. And the last column, lambda n xn. So you see, we can summarize these equations into matrix multiplication. So obviously this matrix over here is the matrix A times X. Now, how can I, forgetting about A for a moment, how can I write, obviously the columns here of this matrix are linear combinations of the columns of of X. What are those linear combinations? Well, if I just multiply the first column by lambda 1, I'm going to get lambda 1 x1. If I multiply the second column by lambda 2, I'm going to get the second column of the result. So forgetting about A for a moment, I see that I can factor this matrix. Now, since these operations are on the columns, the matrix of operations will have to be on the right-hand side of the matrix X. So you see here, maybe I'll take this on a new page. So here what we have is the matrix X and then we want to make some kind of, we want to record what happens, how to get from X to lambda 1 x1, lambda 2 x2, lambda n xn. Well, all you have is multiples. You don't really have you don't have linear combinations of the columns, you just have multiples. So you have a very simple linear combination. So to get this matrix needs to perform an operation, column operations, because it's on the right-hand side of X, this matrix represents column operations. So I want this matrix to give me lambda 1 x1 by using the first column, because the other columns are linearly independent from x1, so I know they don't come into this lambda 1 x1. And the way to do that is to put lambda 1 in the first column and then everything else 0. Okay, so essentially take the first column of the identity matrix and multiply it by lambda 1. That operation is, if you apply that operation on this matrix, it will multiply the first column by lambda 1. So essentially literally do all of this on the identity matrix. Taking x1, x2, xn to be the columns of the identity matrix, that's how you will find this matrix. So immediately you see that you get a diagonal matrix with lambda 1, lambda 2, all the way to lambda n along the diagonal. So what we have here is a times x on one hand and x times lambda on the other. So this is how we get a times x equals x times lambda. Now, because we assumed that x is invertible, so you can write this even if your vectors x1 through xn are not linearly independent. The key to linear independence is that if the vectors x1 through xn are linearly independent, then the matrix X is invertible. So since we assumed that the vectors x1 through xn are linearly independent, we have that the matrix X is invertible. So I can multiply by X inverse on both sides of this equation. So I have two equivalent forms. I can write A equals X lambda X inverse. This was me multiplying by X inverse on the right hand side. Or we can write that lambda equals X inverse AX. Both of these are equivalent equations, although this first one is what we call the diagonalization of the matrix A. Now, of course, I said the diagonalization, but there is a very easy trick or very easy observation to show us that if a matrix is diagonalizable, that doesn't mean it has a unique diagonalization. Why not unique? Well, how can I make, if I know that this works for the matrix A, how can I make a different diagonalization? How can I make a different matrix X? Well, who said I have to order the columns in this exact way? I could rearrange them however I like. They are going to continue to be eigenvectors of the matrix A. But then what I have to do is, if I put x2 as the first column, then I'll have to have lambda 2. Lambda 2 will show up here. So then this lambda 2 will have to move up, right? So changes in the columns of X will have to be reflected with changes not exactly in the columns of lambda, but in the diagonal terms, right? Because if I relabel these things, it doesn't change the fact that this lambda multiplies the first column and therefore it has to be in the 1, 1 position. This lambda multiplies the second column, therefore it needs to be in the 2, 2 position. So we can have actually n factorial different diagonalizations by using the exact same vectors. We could also use multiples of the eigenvectors, because if x1 is an eigenvector, then so is any non-zero multiple of x1. It would have the same, we could take a zero multiple, that too would be an eigenvector, but then we would lose linear independence. So these vectors are non-zero, otherwise linear independence wouldn't make sense. So if I take x1, I can take any multiple of x1. Therefore, this matrix X is far from unique. So it's important to point out here that there is no single diagonalization, but rather the diagonalizations are infinitely many. Now, if you used software to calculate the diagonalization of a matrix, normally what you will get is to get a unique answer, to get the same answer each time. Normally, the vectors x1 through xn are going to be normalized. They're going to be made of length 1. So there you only have, well, you could have plus or minus, right? x1 and negative x1 have the same length. So x1 has the same length as negative x1. So up to this sign change, you have uniqueness. And then what they do is they normally order these lambdas in, say, ascending order. So this would be the smallest lambda, or the biggest lambda could be in descending order. So biggest lambda, and then they order the lambdas. Of course, if you have repeated lambdas, then there is no real way for uniqueness. But if all the lambdas are different, you can order them, and that will fix the ordering of the x's. And so the software will give you this diagonalization in a certain order that can be reproduced. That makes sense for computational purposes. Computers need to know exactly what to do. Computers cannot make choices, whereas humans can. We like one vector better, we'll put it first for no real reason other than because we like it better. So, as I said, this diagonalization is not unique. The way to find it is these guys are the eigenvectors of A. These values are the eigenvalues of A. So if you find the eigenvalues and you find the eigenvectors, which is what we did yesterday, we have a diagonalization for our matrix A. If we have a diagonalization for our matrix A, we have the powers. We have all the powers of the matrix A. Even though we will not always look for finding AN explicitly, but if we wanted to find it, then we would. And, or we could, I mean, from here. And another thing is that, oh, I see here I'm abusing this N a little too much. Maybe I can change the N in the powers here into a K. The reason I say that is because AN, or I'm using N to mean the size of the matrix. So my matrix A is N by N. So just not to confuse the powers with the size, let me say AK here, A to the K. Not to use the notation to mean two different things. So we won't always be looking for that matrix, because as we saw yesterday, we can, if we want to apply this matrix on a single vector, then all we want to do is find how that matrix acts on the vector. It's not necessary to explicitly find the matrix A to the K in order to find its action on a particular vector. I guess I'll close this here. So this will be a theoretical video, and the next one will be on examples. I'll do the diagonalization of a matrix on one or two matrices.